This is the first of 4 videos for this unit we're going to do. We're going to call it Chapter 8, and it's about something that kind of transitions between physics and calculus called the simple harmonic oscillator. A lot of people just call it the SHO for short. In a nutshell, if you're wondering, what's this topic all about? Well, it's all about what happens when you take a mass and put it on a spring. So we've seen springs before, and we know how they work from Physics 11. When you stretch them, they tend to snap back. But if you go and put a mass on there, sure, it'll stretch. But if you take that mass and then go and pull it down and then let go, then it'll go and bounce, much like a guitar string will bounce back and forth when you pluck it. And another issue we're going to see in this chapter is if you take that same spring but put more mass on it, okay, sure, it'll bounce, but it bounces at a different frequency. And we're going to see in this chapter if we can take a look at how the physics and the math relate together so we can actually do a nice job of predicting what that motion's going to look like when we do go and put the mass on that spring and watch it bounce. So let's see if we can dive right into it. On this next page here, I just wanted to start off by saying that you're going to see this issue show up all over the place in engineering. The idea of masses bouncing on springs is something that happens when you try to model a car bouncing on its suspension, or a suspension bridge that's kind of like a spring bouncing back and forth, or the air going in and out of the holes on a violin or a guitar body. Bungee jumpers as well, as they bounce up and down on their elastic cord, they're going to be a simple harmonic oscillator. They're going to behave like a mass on a spring. Even simple pendulums do a pretty good job of behaving like a mass on a spring, bouncing back and forth. Now, I've mentioned that there's a little bit of physics going on in this chapter in addition to the calculus. One thing that we're going to need to be working with for the physics is something back from Physics 11 called Hooke's Law. And so Hooke did some work looking at elastics and springs and how you can stretch them for a little while pretty safely and how they bounce back. And he said that the force from a spring or an elastic when you go and stretch it can actually be modeled by this really simple equation. It's equal to just something called the spring constant, which talks about how stiff it is, and then multiplied by the extension, how much you deform the spring, how much you make it longer, or we're going to see in this chapter how much you compress it, how much you make it shorter. Now we will have to modify this equation a little bit to make it a little more accurate for the calculus world. When you take a spring and stretch it, it tends to pull back and make itself smaller. And if you take a spring and scrunch it, it tends to try to push forward and try to make itself longer. And so actually to model that in our calculus world, we need to put a minus sign on this equation so that if the x is a deformation of the spring in one direction, then the force from the spring is going to be what we call a restoring force going back in the opposite direction. Okay, the next thing that we're going to do right off the start is decide that most of the time we're not even going to worry about the force of gravity. If you actually hang that mass on the spring and then reset your equilibrium to be that naturally hanging position, then you don't have to worry about the force of gravity. So this is going to be what we call the equilibrium position. And it's going to be the place where if you put a meter stick right there, you could say that is position 0. We're going to use x for position here. Sometimes we'll use s, but for now let's use x. And so at that spot there, that's when x is equal to 0. If the mass is ever up above that natural hanging position, then we're going to say, oh, well then up here in this region of space, then the x is actually going to be positive. It'll be in positive position. And if your mass that's bouncing on the spring happens to be down here, then we're going to say that it has a negative position to it. And so I have graphed here the motion of a spring as it goes through one full cycle bouncing on that spring. The first and the last picture are actually the identical picture, just repeated. And there are multiple graphs in the background of all different colors. The blue one is actually going to be the position graph, showing where this thing is located. That's why it actually follows that little blue mass as it bounces up and down. So one of the things I can see, just from kind of comparing that down here, that at the beginning, this first position is going to be right at equilibrium, so the position is 0. Now, the last one over here on the far right, the same story just finished off. But in that second picture, you can see the mass is way up high, and it's up into positive space. So in this particular part of the cycle, you could say, oh yeah, the position, the x value is positive. But then, as you know, the way masses work, when they bounce on springs, they're going to go back through equilibrium. There'll be a brief moment where its position is 0, but it overshoots. It has a lot of velocity, and it actually then bottoms out into this negative space where it's got a negative position to it. And the spring is really stretched out then, and it's going to try to snap it back. Now, the green graph is actually recording how fast that mass is moving at any time. So if you think about it bouncing on the spring, think about the times when it stopped. When is the mass actually not moving? And the answer is when it's way up at the top and when it's way down at the bottom. And you can see that showing up here on this green graph. Right here would be when the velocity is 0. And so this green graph is indeed the velocity for this story. And at the beginning of the story, we'll put the little V on this green arrow here. At the beginning of the story, that object has some positive velocity to it, so it's heading up really fast. And then when it peaks up at the top, when it's got a lot of position, it actually has no velocity, has no kinetic energy. Then the spring, being all scrunched, says, get out of here, mass, and it starts to push it down. And it pushes it and pushes it and pushes it until it gets back to equilibrium. But by then it's got a lot of velocity heading downwards, so you have this big negative velocity. And unfortunately, this mass overshoots the equilibrium position, keeps on going down with this big negative velocity, until it's down at the very bottom in this sort of fourth picture, where the velocity would briefly be 0 as it stops, before it turns around and makes its way heading back up, repeating the very beginning part of the story, where it has a positive velocity. Now, the red graph is actually doing a couple of things. It's going to be force and acceleration. Remember, when you scrunch a spring, it tends to push back out, and when you pull on a spring, it tends to pull back in. So at the very beginning of the story, this thing doesn't have any stretching or scrunching. It's in equilibrium, so it has no force, and there's no acceleration, because acceleration just comes with force. But way up at the top, we have a big positive position. You're going to find that that spring is trying to push you down. So up here, there's a very big negative force, and that negative force creates a negative acceleration. I'm only talking about the spring force. I don't have to worry, and neither do you, about the force of gravity if you've worked from the equilibrium position. It's so nice to do that. In that middle spot there again, when we're at equilibrium, the force is 0. The spring isn't trying to stretch or grow, or scrunch itself down or grow, and you have no force, no acceleration. And then in the fourth story, when we're way down into negative space, that's when that spring is all stretched out. We're going to have an upward, a positive force trying to pull this thing up right there. And we're going to have a positive acceleration as well, until we finally get back to the beginning of the story where we had no force on it and no acceleration. And so it just keeps doing this motion where the spring says, go back to equilibrium, go back to equilibrium, go back to equilibrium, but it keeps overshooting that equilibrium. And even though at equilibrium there's no force on it, by then it's picked up a whole bunch of speed and it slides right on through the equilibrium. Now up at the top of this page here, if you were to watch with a stopwatch for exactly 1 cycle, okay, this would be what we would call on the stopwatch 1 period. So a period is a very special measurement of time, often denoted in Physics 11 by a capital T. It's going to be measured in seconds, and it's the number of seconds you have to wait for exactly 1 cycle to happen. Okay, well, we know that masses bounce on springs. That is not all that exciting. We know that happens, but what we're going to see is, can we go and actually come up with the math for how these things are going to go and bounce on a spring? And it turns out we can. So we're just over here on page 2, and we're going to start to wander through the math for this story and see if we can get the math to agree that this thing really should be bouncing. And there's not a lot of physics that we need to put into the math. We're just going to put in Newton's second law, that net force is equal to mass times acceleration. And there is only one force to worry about, because we're ignoring gravity. We've worked from the equilibrium position, so we don't have to talk about gravity. So the only force to go in is this restoring spring force, negative kx. So there's your differential equation, right? It's the equation that we're trying to solve. It's an equation written in terms of a derivative, in fact, a second derivative. It's a time derivative. And we're going to see if we can come up with the answer for x. Where should this thing be positioned? Expecting that it should be an answer that bounces. Now I'm going to solve for that second derivative, that highest derivative that I see. And when I divide by the m and trade sides, I end up with this second derivative of the position of the thing we're looking for being equal to negative k over m, just some things that relate to the physics of the story, multiplied by x. Now this is a challenge because the thing that you're looking for is x. And there it is, the answer shows up on the right. So we can't just go and undo some time derivatives because the answer is hiding in there. So we're going to have to use our physics knowledge in order to see if we can answer this story. So just thinking about it, apparently two derivatives later, you're right back where you started at x, but you've picked up a minus sign and then this k over m. So my thought here is we need to find a solution, an answer for x, such that, and so this function that we're looking for, it's going to sort of sound like x of t, right, equals some x with t's in it, that after two derivatives, and those are going to be time derivatives, so after two t derivatives, it looks like the function again, but you're going to pick up a minus sign, right, because I can see that, yep, indeed, there is a minus sign here that gets picked up, and maybe some constants. I'm not going to be bothered if some constants show up as well, right, because the physics says that, yeah, there might be some constants in there. So just thinking about the calculus, something you can take two derivatives of, and then you'd be right back where you started, but you'd have a minus sign by then, and maybe some constants. And the answer is cosine does that, and so does sine. And so to speak very generally, we could say, well, how about a cosine with an amplitude, a number out front? So maybe an a multiplied by cosine of, and I'm going to put a number in here too, and I'm going to choose to go with a Greek letter omega, which looks like a w, but it's actually got rounded bottoms, and we're not going to call it w. Okay, it is a Greek letter omega. Okay, so when you can, try to talk about that as being omega. And so these two things here, this a and the omega, those are just some random little constants for now. Well, now I'm suggesting they're random, but we're going to see that it's actually pretty clear what those constants will need to be. So that's one option. We'll get to the sine one in a minute, but let me show you why I believe this is a good option. Let's try doing two time derivatives, because remember, the differential equation says this x double prime should look just like x. So let's make our way there. After one derivative, the cosine is going to convert to a sine of omega t, and omega will show up from the chain rule out front, and so will a negative. So you'll have negative omega, and then the a just spectates and hangs around. But we're not done yet. That's only one derivative. Now we've got to do a second derivative. When we do our second derivative, the sine converts back to a cosine. Another omega arrives, but not another minus sign. And so you would have minus omega squared a cosine of omega t. Now here's the part that's super important. This section of it, a cosine of omega t, that is what we started with. And so this has done exactly what we wanted. After two derivatives, we're back to where we began. But we've picked up a minus sign and some constants. Okay, so the minus sign, I can see it here. Yep. And some constants as well, right? There's this math constant showing up, this omega squared. Not only does cosine do that nicely, but so does sine. Let's put another random amplitude up front. We'll go with capital B in this chapter. And then omega t, same omega. So what if that was the position for x? You would take a derivative, and an omega would arrive from the chain rule. The b would spectate, and the sine would convert into a cosine. Well, you do one more derivative, and you're going to find that you pick up a minus sign now, and another omega to join the one that's out there. The b is still hanging around, wondering what's going on, and then you would be back to sine of omega t. And so sure enough, this is also good enough. It satisfies this condition that after two derivatives, I'm back to where I started, but I've picked up a minus sign and some sort of constant. So let's see if we can figure out what's the deal with this omega. Why are we using this Greek letter? Well, it turns out it's kind of a Math 12 issue with transformations for sine and cosine. So in the engineering world, we would say that omega is what we call the angular velocity. It talks about how fast this thing is going to bob up and down and how fast the graph of it would bob up and down if you were to graph it, but it's not measured in meters per second like a normal physics velocity. It's measured in kind of Math 12 radians per second. And if you're wondering, well, how do I figure out what this omega should be in order to get the right math graph? Well, all we have to do is realize that the omega that's showing up here from the calculus, that omega squared, has to be the same as this k over m that's up there in the physics story. So if we put the calculus and the physics worlds together, we get negative omega squared is equal to the negative of k over m. The left side comes from the calculus. The right side comes from Newton's second law. Well, you don't need the minus sign. You can toss that, and then you can take a square root. And if you're wondering, well, what's the right omega that talks about how fast these graphs of the motion are going to bob up and down, then it's going to be the square root of k over m. And so that's how we can find this omega value. It's measured in radians per second, and it's going to talk about how quickly it bounces. Now, this maximum values little spot here, the first time you see this, and maybe the second and third time, it's a little confusing. But then all of a sudden, at some point, you're going to look at it and go, oh, I get it. That's super handy. So I'm going to start showing it to you right now. If you take a mass on a spring and pull it down and let it go, that amplitude that you've got right when you let it go, that would be your biggest position. That's going to describe how much this thing bounces back and forth. You can measure it in meters, right? How much are you going to pull this thing before you let it go? If you're wondering, I wonder how fast this thing would ever get. Let's call that Vmax. And if you're wondering, I wonder what the most acceleration would ever be that this thing would experience. Let's call that Amax. These are super easy to find, and all you have to do is look up at the top of the page here, because if A is the number that's sitting out front here about the amplitude for your motion, then when you're looking at how big the amplitude is for the sine graph, it's actually the same thing that you put in that A, but now you've picked up an omega. And then when you go to look at how big the cosine acceleration would be here, the amplitude would be the same A that you decided when you pulled the thing down, that biggest position, but now multiplied by an omega squared. So the biggest velocity you'll ever see once you pluck that guitar string or pull the mass down, it's actually equal to nothing but the omega value, which you can find, it's just the square root of k over m, multiplied by that biggest position, that x max. And if you want to know, well, what's the biggest acceleration number I'll ever see? Just take your omega, square it, and multiply it by your biggest position. So you decide the biggest position when you pull it down and you let it go. And now you're also going to see that that decides what the biggest velocity and the biggest acceleration would be. And yeah, it does depend on the mass and the spring. But if you have that value of the square root of k over m, it's so easy to find those. Now, the last two things on this page, let's just go and talk about converting this omega thing back to the world of physics. Let's look at the period of the motion for a minute. So just a reminder, period is just a time measurement, but it's a time for one cycle. Exactly one cycle. And when you've reached a time of day that's equal to one period, looking back at these graphs up here, that's when the material going into the input of these trig functions, this omega multiplied by t, what we call the argument of the function, that's when that omega t at that value for little t will have finally reached 2 pi. So for one full cycle, that's when omega multiplied by that very special time, so I'm going to call it a capital T now instead of a lowercase random t, that's when you'd hit 2 pi and you've gone through one cycle. So if you're wondering, well, how long will it take for this thing to bounce? The answer is 2 pi divided by the omega. And if you're wondering, well, what's the omega? You already know. It's actually just the square root of k over m. So if you know the spring constant and the mass, you can now find how long it'll take to bounce. And that's great if you want period, but if you'd rather talk about frequency, like good old physics 11 frequency, frequency is 1 divided by period. So we could take this equation for period and just kind of trade it around a little bit and say, oh, okay, frequency would be that flipped upside down. So it's the omega divided by 2 pi. That's like a frequency measured in hertz, if you wish. Now, most people take this and they just remove the fractionality of it and say, hey, why don't we write this as omega is equal to 2 pi f? A pretty common thing for you to start remembering when you're doing your mechanical engineering. That relates the omega, kind of the math calculus world of this description, to the hertz, the frequency that you know from your first course in physics. Okay, one more page of general theory for today and then some fun. The general solution. So I'd mentioned, I'm going to go back, that up here at the top of the page that, cosine would be a good way to describe the motion. And then I put in the word or sine. Sine would describe the motion. Well, it turns out that the general solution would actually say, well, why not both? Why can't they both be involved? So that's probably worth a little note in here. The general solution, this includes both the cosine and the sine. So the most general solution for a mass bouncing on a spring is going to be some sort of amplitude, some A, some number that we'll decide. I'll show you how to find that in a second, multiplied by cosine of an omega multiplied by t. So remember, I promised you would come up with an equation that has t's in it, right? So we can describe the bouncing. Plus, and then possibly another number here, a b, multiplied by the sine of omega t. And it'll be the same omega. So we've got some red things that we'll have to go and find for any given story in order to truly describe the bouncing. So let me offer you some advice for how to do that. First thing, we're going to talk about m as being the mass of the item that's bouncing on that spring. Okay, we're going to measure that in kilograms. The K is the spring constant from Physics 11. It's really a measurement of the stiffness of the spring. A stiffer spring has a higher spring constant. And the equation that we use, good old F equals kx, is kind of what you might know for using that, suggests that the units would be newtons per meter. Omega, this is that angular velocity, and you can calculate it by doing nothing but the square root of k over m. Okay, so that's our angular velocity. It's a way of describing bounce rate that's really, really useful for graphing. The units for it, radians per second. Capital A. Let's see if we can figure out how you would know what capital A is if you're going to try to use this equation up there at the top of the page to describe the motion. Well, let's actually go and look at the top of that page there for a second, look at that equation. What would happen if you were to try out a value of t equals 0? Let's just think about that for a minute, like time of day equals 0. If you were to go and substitute into that story up there at the top of the page, t equals 0 in here and in there, of course multiplying by omega won't change anything, it'll still be 0. And you'll have a cosine of 0 and a sine of 0. Cosine of 0 is a 1. It survives, gives you a good healthy answer, but sine of 0 is 0. And so the capital B goes away, but the capital A would stay around. And what that tells me is that if you're wondering, well, what is this capital A? Like, how do I know what to put into the equation for that? Capital A is going to be the initial position. So when you grab that mass and you lift it up above equilibrium or you pull it down below equilibrium, if you measure how far you are from equilibrium, measured in meters, that's the number that needs to go in for the A. It's sometimes written as x naught, okay, the position at time 0. Okay, so A is the initial position. What about sine? What's going on there? Well, it turns out there's more than one way to start a mass moving on a spring. in addition to pulling it down and letting it go, like plucking a guitar, you could have had it at equilibrium and then walked up to it and given it a little flick, a little tap. And if you tapped it, you'd be giving it some initial velocity. So let's imagine looking at not this equation for x, but right underneath it, I'm going to scribble in the velocity equation. Velocity would be a derivative. So an omega would show up. I would have minus omega times a, and then sine of omega t, plus, and an omega would show up, omega times b, and then a cosine of omega t. Now once more, imagine putting in t equals 0. The cosine turns into a 1 and survives, but the sine turns into 0. And so at time 0, you would have omega times capital B. So omega times capital B, that must actually be the initial velocity. Now, when you first start your mass bouncing, maybe you choose not to have an initial velocity. Fine, then you won't have a value for capital B. But if you choose to have an initial velocity, then you need a capital B value. Okay, that'll be the initial velocity. Maybe I'll call that V naught. Now, often we rearrange that and say, oh, well, if you want to then find out how big B should be if you're trying to graph the motion, just take the initial velocity, if you choose to put one into your motion, and divide by the omega. So we're now totally ready to go. We're ready to find the equation that will describe the motion for this object as it bounces. Okay, this equation up here, it'll depend on the mass and the spring that shows up in the omega, and it'll depend on how you make it go into motion, whether you pull it down and let go, or whether you pull it up and let go, or whether you give it a little flick upwards or downwards, and those are going to go in for the capital A and capital B values. And that should be enough, except there's one issue. Sometimes we lie to you and we tell you that, oh yeah, it's super simple, and then you realize, well, actually there's a little more to the story. It turns out if you watch a mass bouncing on a spring, the mass is not the only thing bouncing. The spring is too. Well, let's say this. Part of the spring is. The top coils aren't bouncing at all, but the bottom ones sure are. And you have to include the spring's mass when you're trying to figure out how much mass is actually bouncing. And you might think it would be reasonable to think that you'd include half the mass of the spring, but it turns out it's like a kinetic energy issue, and you have to do some integrating. And it turns out that it's a little more complicated, and you actually need to include 1/3 the mass of the spring in your calculation for the total mass. This is the mass that you're going to use when you say, oh, omega is equal to the square root of k over m. That's the mass that will go in there. The main mass plus 1/3 the mass of the spring. That's going to be important for us on the next page here when we try to get just the right mass to bounce at just the right speed. We'll have to remember that the spring is also there too, and it will actually kind of affect our story as we go through it. So that's the theory for actually the first half of this little chapter. And now there's no homework with this one, but there is some playtime. So we're going to do a couple of pages of just nothing but play. But before we do, I need to know what the spring constant is for this particular spring that we're going to be using. And so for this spring, when I wanted to find the spring constant, I tried just taking a mass and then hanging it on to the end of that spring. And I noticed that at the beginning, it was just a little bit more than 51 centimeters long on this ruler and then stretched down to about 64 to where the end of the hook was. And that's when I put 200 grams on there. So with a mass of 200 grams, or I guess 0.2 kilograms, the weight of that is 1.96 newtons. Now I know I said a minute ago, you never have to worry about the actual force of gravity, and that's true for the bouncing part, but we can use the force of gravity when we hang things to find spring constants. So when I added 1.96 newtons of weight, what I noticed was this spring actually stretched. It stretched by almost 13 centimeters, right? I think it was actually about 12.8 centimeters or 0.128 meters. I think that's what the number was. I'm just going to try a quick division here. this going here for you again. Oh, hang on. Lost the page. There it comes. So 1.96 divided by 0.128. Yeah, it's around there. Now, I have to tell you that for the work we're going to do, we're going to have a little fun with this, but we need values precise to about 4 or 5 sig figs. So I used a different method to do an even better job measuring this K, because that 12.8 centimeters of stretch just wasn't good enough. And I found that the spring constant, best I could measure, was 15.35 newtons per meter. It's consistent with what we can see as we stretch it with the 200 grams, but I needed a little more precision for the work we're going to do. And here's what I did. I wanted to see whether I can get a mass, not 200 grams, but a pop can with some water in it to bounce to the beat of a song, so it looked like the pop can was dancing. And so I need to know the frequency that I'm trying to target. And so you're going to do this as well with a song of your choice in a week or so. So I took a song and I got the song rolling, and then while I was listening to the song, I actually listened for some part of the music. It could have been perhaps maybe the cymbal. Maybe I'm counting on every beat and I'm sitting there listening to every single beat of the music and kind of tapping my finger to that. Or maybe instead of doing that, maybe I might want to listen to the snare drum, right? And count on the snare drum and kind of tap my finger to that music. Or if you don't want the snare drum, then maybe the kick drum, maybe the bass drum. So you're kind of listening to the music and trying to kind of tap your finger to that part of the music. But you have to very, very carefully count for a whole bunch of beats in order to figure out what the frequency of this music is. Now, I listened to the snare drum on this one, and after sinking my finger up to the snare drum and then counting for a very long time, I counted for 50 beats. I then looked at what my stopwatch was saying. So you'll need to use your stopwatch on your phone so you can be counting. And you have to make sure that when you first start your stopwatch, you have to say 0 to yourself, not 1. So especially if you're in music, you're going to be tempted to say 1, but it hasn't cycled once yet. So when you first turn the stopwatch on, as you're tapping your finger, you have to say 0 and then count from there. 1, 2, 3, until you get to wherever you'd like to stop. I would suggest at least 40 beats, maybe 50 or 60. And for this song, for the Blues Brothers, Sweet Home Chicago, I found that the time, and I did it a few times to make sure I was happy with my time, I had 48.05 seconds for 50 beats. And so I then took my calculator and said, okay, physics 11, I've got 50 cycles in 48.05 seconds. What do we have? And I had a frequency, and don't hold back. Go to like 4 sig figs here, maybe 5, right? You're going to need a lot of precision in order to get this to work. I'm going to see if I can actually get a harmonic oscillator, a mass on a spring, to bounce to the beat of the music, and it has to have that frequency exactly. Now, the mass that I'm using can only have a range of masses on it from fairly small until they're about to fall off until something big that might damage the spring. So when you go and do this as an assignment, you have to shoot for a frequency between 0.9 and 1.8 hertz. If it's more or less than that, you'll have to either double or half your frequency in order to get it to work, kind of like cut time. Basically, instead of counting every beat, maybe count every other beat, because we don't want to have a frequency that's higher than 1.8 or lower than 0.9. Mine fits in there quite nicely, so I'm actually going to use this value. But I would see different numbers in this little exercise if my frequency was, maybe my frequency might have been 3 hertz. It's a really fast song. And I'd go, oh, well, 3 is too high. And I'd cut it in half and say, what about 1.5? Ah, yeah, 1.5 would be fine. So I'm going to shoot for a simple harmonic oscillator frequency that actually is just the same as my frequency of my music. Okay, here's the calculation. The omega is like the math 12 frequency, and the F is like the physics frequency. So we need to do some converting here. So the omega would be 2 pi times this 1.0406. Okay, well that's still on my screen, so times 2 pi, 6.5382. Just a different way of talking about how fast this thing is actually bouncing. That's going to be measured in radians per second instead of cycles per second. All right, now here comes the important calculation. Your goal is to try to find the mass. What kind of mass would you want to hang on that spring in order to get it to bounce to the music? So we're looking for that total mass. The omega, we know based on the music, and the K, we know because it's just the spring that we're going to be using. So I would have 6.5382 is equal to the square root of, now again, this spring constant, 15.35. And when you go to do your assignment in a couple of weeks, it'll be that value too. Then we're going to go and look for this total mass. I would square both sides. Just get rid of that root, right? So if I square that, 42.7477. That would equal 15.35, all on top of the total mass. Okay, I'm going to multiply by total mass, divide by the 42. If I go 15.35 divided by that, it looks like my total mass needs to be, this is in kilograms, 0.35908 kilograms, or 359.08 grams if we want to talk chemistry units. Now there's a catch though. When I go to make a mass to try to hang on this spring, I have to remember that the spring is out there too, and 1/3 of the mass of the spring kind of comes along for the ride. Let me tell you that the mass for this spring, it won't change for when you do your little demo as well. It's 65.57 grams, or 0.6557 kilograms. Okay, now I'm going to go and see if we can find the mass of a little can of water that would actually work, that would give us just this perfect bounce. So I would have 0.35908. It's going to be the mass of a little can of water plus 1/3 of 0.06557. Okay, so I just have to do a little subtracting here now, and then this thing's ready for testing. So minus 0.06557 divided by 3. Okay, take 1/3 of that. 0.33723. That would be kilograms, or 337.23 grams. Somewhere around there. Okay, so then the next task is to go and very, very carefully pour out some water into that can until I get as close as I can, just dribbling drips of water so they can only do a drop at a time. I got as close as I could to 337.23, do within one drop, and then you go and you take that mass and you put it on your spring and you cue the music up. And now you have to teach the mass where the beat is. So you have to kind of let it go at just the right time. And if you do, then that mass will sit there and bounce to the beat of the music. So the little logo on the side is a bungee jumper. He's hanging on the end of that spring. It's Bob the bungee jumper. And your goal is to make Bob the bungee jumper kind of in the air, hanging on the bungee cord, bounce to the beat of the music. Now if you want that bungee jumper to stay in time with the music for like 10 or 20 or 30 beats, you'll have to be precise down to about 3 or 4 sig figs. So you really, really have to work at doing your counting very, very carefully And a couple of weeks down the road, we're going to do a little assignment where you get to see whether you can actually count your song close enough. And then I'll test it here and then play the video of your song being tested so you can see if it works. All right, so that works so well that I think we should do it again. So just for fun, we're going to do it one more time because it's just too cool. So one more time, same spring constant. Okay, that's not going to change. 15.35 newtons per meter, but a new song. So I'm not going to tell you what the song was. I'm just going to tell you, I'll show you in a second. I'm just going to tell you that this time, to be really precise, I counted for 60 beats. And when I counted for 60 beats, stopped my stopwatch. I was so careful when I first turned the stopwatch on, I had to say 0. And it's so tempting to say 1 when you first start counting those beats. But I had to say 0. And for me, it was 58.92 seconds for 60 beats to go by. So I'm curious to know, well, what's my physics 11 frequency? 60 cycles divided by 58.92. And you want to be like trying it out a few times so you can have this to hopefully 3 or 4 sig figs. So 1.0183 hertz, somewhere in there. And now I'm going to see if I can get this mass to do its bouncing. So frequency adjustment, I don't think there's a problem here. My music was 1.01833. That's within the range, so things are good. I don't have to cut it in half. If I was, I'd just write the new number here, cut in half. But this should work fine. Okay, I'm going to go for that as my target frequency. And now I've got to convert to the calculus world. So calculus likes to talk about omega. Not a problem. We'll just take our physics frequency and multiply it by 2 pi. You'll do this so many times at university now. You'll be working almost continuously with these omegas. They just work better for the calculus. So we'll times by 2 pi. 6.39835. I already forgot the number. 3983536, somewhere in there. And now we're going to go and see if we can find what would be the right mass. So 6.39836-ish is the square root of 15.35 divided by the mass total. Going to square both sides, get rid of that root. 40.9389. That would be the spring constant number divided by the total mass. Okay, so the total mass would be 15.35 divided by that last answer. All right, total mass, but this includes a portion of the spring itself. 0.37495-ish kilograms. Okay, quick little calibration to deal with the fact that the spring is actually bouncing around and I have to anticipate 1/3 of the mass of the spring, kind of changing that measurement. So 0.37495 is going to be the mass of my little can of water plus 1/3 of decimal 0.6557. Okay, so subtracting off decimal 0.6557, cut by 1/3. 0.35309. Okay, and as I finish this off, I just want to let you know there's no homework for this first day. Just sit back and enjoy this one. But think about what song a couple of weeks from now you're going to want to do as an assignment. This is one of the 2 assignments for the chapter. And that's a couple weeks down the road. And you'll basically do this, and I'll test it for you and then make a video of whether or not yours worked or not. But this should be the right mass for this one. So I did the same thing. I went to the scale, and as best I could, I hit 353.09. This one worked pretty well. And then it was time to test it out. So you take that mass, you put it on the spring, and you get your music going, and then you just have to time the release just right. So enjoy that, and there's no homework at this point. Then next day we're going to take a look at a little more theory with this, and just do some more grinding out of some numbers, and then I will show you just how the assignment will work a week from now when we start to do this.